Hi there. In this video, we're going to talk about the inverse Laplace transform. So thus far, we have seen that we take the Laplace transform of some kind of function, for example, sine of 80, and according to our standard transforms, which we had seen in the previous videos, this is equal to a over s squared plus a squared. So what we're talking about now is that if we are given the Laplace transform, can we somehow determine the original function that had come up with this Laplace transform? So what we're asking for is the inverse of the Laplace transform. So we write that as L to the minus 1. So we want the inverse of the Laplace transform of a over s squared plus a squared. So in this case, it's sine 80. So this does not mean that we're taking a reciprocal or something like that. It just means that we're taking the inverse of this Laplace transform to find this original function. So it's easy once we have these kinds of standard transforms. So another example would be the inverse Laplace transform of 1 over s minus 2. So you would recall that the Laplace transform of e to the power 80 is equal to 1 over s minus a. So this is what we're given. We're given the inverse now of this 1 over s minus a. In this case here, this a is 2. So our original function is e to the power 2t. We just replace this a with 2. And we can carry on in this manner of finding the standard transforms. It sometimes gets a bit more difficult now if we have more complex types of functions where it's not easy to see. But before we look at that, maybe just an extension of this example is if we have two terms, for example, 1 over s plus 2 plus 2 over s minus 3. So this would be e to the power minus 2t. In this case here, the a is minus 2. And it would be plus 2 because of this 2 here on the top. Then e to the power 3t. So of course, this means the Laplace transform of e to the minus 2t is 1 over s plus 2, inverse. So now what if we are given a function where it's not that quite simple to see? For example, we want the inverse Laplace transform of 5s plus 1 divided by s squared minus s minus 12. So this doesn't actually form part of our standard Laplace transform tables. We cannot just go and see, okay, what does this correspond to, and find the function just by inspection like this. So what we have to do is we have to put it into this kind of form. We have to split this function to be in terms of some kind of function with which we can actually take the inverse Laplace transform of, basically put it into some kind of standard form. So the way to do it when we have it of this type here is to use partial fractions. So what we essentially do is split this fraction into two terms, as is in this previous example. So there are some rules of partial fractions that we need to be aware of to be able to apply it. And the first rule that we should note is that the degree of the denominator must be greater than the degree of the numerator. So we can see that in the denominator, it's of order 2. And in the numerator, it's of order 1. So obviously 2 is more than 1. Therefore, we can use this method of partial fractions. So the rules of partial fractions are that, okay, if we have some numerator k divided by s plus a and then s plus b, then we can split this into two terms, a, coefficient a, over s plus a plus b, a new coefficient b, divided by s plus b. Another rule of partial fractions is, let's just say now we have something like k over s plus a squared. So what this will look like is the coefficient a divided by s plus a plus b over s plus a squared. So if we had cubed here instead of squared, what we would do is we would just add another term plus c over s plus a cubed. It would carry on in that manner. So there's just one more rule to be aware of, and that is k over, just write that a bit better. So we have k over s plus a into s squared plus ps plus q, where p and q are just coefficients of this quadratic part of this denominator here. So what this would look like is that we would have this s plus a. So we can have s plus a like that, associated with this coefficient capital letter A. Now we will have this quadratic term s squared plus ps plus q in the denominator of the second term, but in the numerator, instead of having just a single coefficient like a, instead we'll have thus bs plus c. So this b and this c are both constants like that. So if we now apply this to our example, we can just go back to our example, and it was 5s plus 1 divided by s squared minus s minus 12. So we're now going to put that in the form of partial fractions using this rule that we had just shown. Let's just take out that fraction and let's just split it. So this was 5s plus 1 divided by s squared minus s minus 12. So the first thing that we have to do is to take this denominator and factorize it. So we have 5s plus 1, and when we factorize that denominator, we get s minus 4, s plus 3. So we can now see that is in the form as we had shown. So we separate it out. We have two coefficients, a over s minus 4 plus b over s plus 3. So what we're now going to do is this equation, we're going to multiply both sides by this denominator of the term you see on the left-hand side. So we're going to multiply both sides by s minus 4, s plus 3. So if we do that, we're going to get 5s plus 1, which is equal to a into s plus 3 plus b into s minus 4. So we need to solve for these coefficients a and b. So the technique to do that is to just substitute values of s and then solve for a and b. So what we're going to do is we're going to substitute s is equal to 4. So if s is equal to 4, we put that in. 5 times 4 is 20. 20 plus 1 is 21. And then 4 plus 3 is 7. And 7 times a is 7a. And then we go here. 4 minus 4 is 0. So this thing is times 0, and b is just going to be, this term is going to become 0. So that's why we did it. That's why we substituted s is equal to 4, because we were able to get rid of this b from this equation. So what this means is that a is equal to 3. So we can substitute another value for s. So we'll now substitute s is equal to minus 3. So 5 times minus 3 is minus 15. Minus 15 plus 1 is minus 14. And minus 3 plus 3 gives us 0. So this a term is gone. And then we have minus 3 minus 4, that is minus 7. So we have minus 7b. That means that b is equal to 2. So this inverse Laplace transform of 5s plus 1 divided by s squared minus s minus 12, that is just equal to the inverse Laplace transform of a, which is 3. So we have 3 over s minus 4 plus b, which is now shown as 2, 2 over s plus 3. And we have this in a standard form. So this is just equal to e to the power 4t with the 3 in the front plus 2e to the power minus 3t. And that's how we would do it. However, there's just one more thing that we can mention about this, and that is a shortcut. So that shortcut is the cover-up rule. So this shortcut essentially allows us to get these coefficients a and b through a kind of shortcut. So we said just now that 5s plus 1 over s minus 4, s plus 3, and we wanted to determine those coefficients a and b, and we had over s minus 4 and s plus 3. So the shortcut is this. For a, okay, we look at this expression on the left-hand side. So what we're going to do is we're going to block out this linear term that's associated with a, and that term is s minus 4. So we're going to look at on the left-hand side, and we're going to block off s minus 4. That's what we're going to do. And then we're going to write what's left. And what's left is 5s plus 1 over s plus 3. And we're going to take the limit of that, we take the limit of this as s approaches 4. So we blocked out this s minus 4, we wrote what's left, and s minus 4, now we took s is approaching 4, right? So it's the kind of the conjugate of this minus 4. So if we do that, what we get is 21 over 7, which is 3. That's a. Okay, we go up, we had seen that a was 3. So to determine b, we do the same thing. What we do now is instead of blocking s minus 4, we block s plus 3. So there's s minus 4, and now we just block out this s plus 3. We write what's left, so that's 5s plus 1 divided by s minus 4. And we take the limit as s now approaches minus 3. So what this is minus 14. 5 times minus 3 plus 1. Then minus 3 minus 4 is minus 7, which is just 2, which is what b was equal to, as you can see here on the top. So this is essentially a shortcut for establishing these coefficients a and b. So they only work if this kind of fraction that we're taking is in this particular form with these linear coefficients like this. So in this video, we spoke about the inverse Laplace transform, and all this essentially entails is looking at what expression we have, the transformed expression, and trying to find what kind of original function gave us that Laplace transform. And we saw that when we have complex fractions, or we have to now use partial fractions to determine what the expressions are, and then we can take the inverse transform like that. So thank you very much for watching.